Hello and welcome to Textbook Engineering Problem. We are working on Elementary Principles of Chemical Processes, 3rd edition. We're working on problem number 2.25. The problem says a seed crystal of diameter d in millimeters is placed in a solution of dissolved salt and new crystals are observed to nucleate form at a constant rate r in crystals per minute. Experiments with seed crystals of different sizes show that the rate of nucleation varies with the seed crystal diameter as this given empirical function r equals 200 d minus 10d squared, where d is in millimeters and r is in crystals per minute. Okay, I don't want to write crystals every single time, so I'm just going to say C stands for crystals and minute. Okay, part A says, what are the units of the constants 200 and 10? Assume that the given equation is valid and therefore dimensionally homogeneous. Okay, so what you have to understand is that when you have an equation, each term in the equation has to have the same units. So in this function, r has the same units as 200 times d minus 10 times d squared. Each one of those terms, there's 3 terms, each one of them has to have the same units. We already know what the units of r are, so now we can calculate what the units of 200 and 10 are because we know the units of d. So, okay, so in order to calculate the units of 200, you have 200, these units are unknown, we don't know what those are, times d, but we do know the units of d are in millimeters, and we know that altogether it equals the units crystals per minute, because it has to be the same units that the units of r are. So now we can calculate what the units of d are, or the units of 200 are. So units of 200, we don't know what they are, times millimeters equals c over m. And now you can see that it's just a simple algebra problem and figure out what the units are. The units are c over minutes times millimeters, because you divide both sides by millimeters. So those are the units of 200. Now we do the same thing for what are the units of 10. So units of 10, we don't know what those are, but we do know that d squared will have units of millimeters squared. Again, we're looking at this unit, and we know that that unit has to equal c per minute. Okay, so now we just divide both sides by millimeters squared, and we get c over minute per millimeter squared. So those are the units of 10. And these are 200 unit. Okay, so that's the part A. For part B, we have to calculate the crystal nucleation rate in crystals per second corresponding to a crystal diameter of 0.050 inch. Okay, so now our equation is only valid for certain units. Well, now they want us to calculate what the rate is in different units using inches instead of millimeters. Okay, so in order to use our equation, d has to be converted into millimeters. So they gave us d in inches. Let's convert that into millimeters. 1 inch, there are 25.4 millimeters, and this equals 1.27 millimeters. Okay, so now we plug that into our function. 200d minus 10 d squared equals 237.9 crystals per minute. But they want us to convert this into crystals per second. So R in crystals per second equals 237.9 crystals per minute. 1 minute has 60 seconds, and minutes cancel, and we're left with crystals per second, and this equals 3.96 seconds. Okay, now part C, derive a formula for crystals per second in terms of d in inches. So now instead of converting our inputs, we're converting the equation. We're converting our machinery in order to just straight calculate from inches. You can often see this in industry when if you commonly get units measured back from a laboratory or from your own measurements out in the field, and you have this equation and you're sick of converting your inputs every single time. Well, you can just change your function, update your function so that you're getting the function in the units that you want. So let's say that A is our new unit of 200. So I'm rewriting our equation to say R equals A instead of 200 times D minus B, a new parameter that's it's going to replace 10 d squared. Okay, so A is a replacement of 200, and we're shifting the units, so the units of A are going to be different from the units of 200, but it's still going to have the same property values. So 200, and we said that the units of 200 were C, or crystals per minute millimeter. Okay, so crystals minute millimeter. We need to convert this into inches and seconds. Okay, so 25.4 millimeters in 1 inch, and 1 minute there are 60 seconds. So that means A equals 84.7 crystals per, crystals per, minutes cancel, millimeters cancel, so inch second. So that's what A equals. And now B equals 10 minute times millimeter squared. And we're going to convert this to 25.4 millimeters, but this has to be squared, and inches squared, and 1/60 seconds. Okay, so now we pull out our calculators, crunch these numbers, and B equals 108 crystals per inch squared times seconds. Okay, so we've successfully changed our machinery. Now our equation will accept units of inches and output units of crystals per second. So let's pull out our calculator and calculate what the new R is using this function. And I got 3.96 crystals per second. And that is exactly what we wanted there. Oh, I just noticed that that is supposed to be crystals per second. I had my units mixed up. Shouldn't have done that because this whole problem is about converting units. So, all right, great. Thanks for joining me on Textbook Engineering Problem. If you guys have a request for a problem that you're doing in this book that you're having problems with, I may be able to figure it out and make a video on it. So just let me know in the comments if you guys have a request, and I will try and get to that and post a video about it. Anyway, thanks for watching, and if I made any mistakes in this problem, let me know in the comments and I can make an adjustment. Great, thanks, bye.